Okay, shall I start? Okay, welcome everybody to day 3 of this conference. I am gonna be a chair today. I'm very excited. I mean, the talks look, yeah, really promising. So let me start introducing our first speaker today, which is Kevin Ellis. He's an assistant professor in computer science at Cornell, and he has spent the past year as a research scientist at Common Sense Machines. And before that, he did a PhD in cognitive science at MIT. He works in artificial intelligence, program synthesis, and machine learning. So I cannot wait to hear you, Kevin.
Thank you for the introduction, Natalia. So I'm going to be talking about scientific models, discovery, and how higher level forms of knowledge can come into play in this picture. And in this talk, I'm going to be taking some very specific stances on how to operationalize these goals in computational terms. So in particular, I'm going to be thinking of scientific models as a kind of generative program. As a consequence of that, discovery is going to be implemented as a kind of program synthesis, and higher level knowledge is the kinds of systems of knowledge that allow you to discover new programs and relate them to data and theory is going to come in the form of a hierarchical Bayesian prior over programs. So I think that it's best for me to not explain this in text, but to show some pictures from some work that was done a little while ago by a cognitive scientist, Tomer Ullman. What Tomer did is he asked the question of, well, what would it mean to understand the physics of balls that are bouncing around in some scene, and like maybe they attract each other, or maybe they have like these colored boxes that they can glide over. Maybe they interact with those colored boxes in some way. In order to make sense of this, if you saw some video of these objects interacting, you would need to know their initial conditions. And you would also need to know something about the properties of those objects, like what objects attract each other, what obstacles have high friction, what ones don't. And you could write down little programs that would explain the initial conditions, and which would explain for any given initial conditions, what are the forces and properties of these objects. And so in some sense, these kinds of knowledge live at different levels. This level of the data and the initial conditions, which just are used to describe the data of a particular video. And then at a higher level, there's more generic knowledge about what the properties and forces are within this world. And you can keep on pushing up this hierarchy of knowledge and talk about maybe the types of objects. You can talk more about the kind of schemas for different force laws, like are they pairwise laws or global force laws. And at the very highest level of knowledge, you have things like the idea of objects with properties and dynamics that evolve over time by integrating differential equations. So really there's a hierarchy of knowledge, and to understand any one data set, you have to operate at all of these different hierarchies. And if you look at what scientists do, they really operate at every level of this hierarchy. So why am I interested in describing these as programs? So I want to motivate that also. So one is that if we think about scientific theories, what's really amazing about a scientific theory as opposed to just mere curve fitting is that theories generalize far outside the range of data on which they are originally based. And the kinds of things we build with programs, by virtue of being algorithms, are sort of designed to generalize. The other reason why you might be attracted to programs is because they are the kind of representation that human scientists and engineers use in order to communicate formal knowledge about the world. So you can see this, for example, in how 3D objects are designed. If you have something like a CAD program with parts, it's much easier to decompose and interpret and remix in new creative ways than the analogous point cloud or mesh representation. But really the most celebrated feature of programs is their Turing completeness or their universality. And I think that if you think especially about like discovery problems, you're only interested in a discovery problem if you don't kind of know what the solution looks like. So you need a representation which is rich and expressive, or else it just doesn't even make sense to be doing discovery. So the main challenge here is combinatorial search. If you want to synthesize programs, programs are these discrete symbolic objects. You don't have a nice gradient signal to steer you toward the right kinds of programs, which would both explain your data and generalize well. So if you want to try to take this path of explaining data and discovering models through program synthesis, then combinatorial search is the very first problem that you encounter. So I'm going to structure this talk around two examples of higher level knowledge. One is going to be a case study in computational linguistics, which will help motivate why we would even care about this. And the other is going to take a core idea from that case study in computational linguistics and generalize it to other kinds of program discovery. So I'll start with the linguistics work. And I want to point out that these other sort of well-known examples of automated scientific discovery often frame what they're doing as some kind of program discovery or some search over algebraic expressions or logical forms. But usually what they do is they focus on a particular data set. So they say, like, I have this data set and I want to figure out like what is the Lagrangian for this system. And scientists certainly do look at individual data sets and say what's the best formal account of what's going on here, but they do something also that's much more interesting, which is they pop up a level and ask, like, what is the general system of stuff that can make sense of lots of different data sets. And if you think about natural language, we're actually in a very similar boat. We have this smorgasbord of natural languages, and they're all very diverse and very interesting, but they're also kind of united at the highest level through these other higher level forms of knowledge, which in linguistics are called universal grammar. So these are kind of the core principles that span multiple languages. And this work that I'll be talking about is joint work with a combinational linguist at McGill, Tim O'Donnell. So I want to give an example of what I mean by discovering models of natural language. So imagine that you see the following data from Mandarin. You know that there's some word that as an adjective is man, as an adverb is manmanda. There's another word that starts out as how and becomes howda. If I tell you there's a word called kwai, you should just think to yourself, like, what would be the natural reflection of this word? And probably you're thinking kwai-kwaida. And if you're a linguist, you might explain this pattern by saying you take a stem, you append it to itself, and you add da. So that was very easy. And I'll give you a more complicated example. Imagine that you have some data from Serbo-Croatian, which is Bogat goes to Bogata, Blag goes to Blaga, and Zelen goes to, you should think to yourself, well, of course, it's Zelena. And you could write a little program which just says add on to make this word feminine. Now, you can also do this backward. So I can give you the feminine form like Yasna, and I can ask you, what is this masculine form? And probably you think it's something like Yasin, but it's actually Yasan because there's this other pattern in Serbo-Croatian, which is that you insert an a between word final consonants. So there's entire textbooks full of these kind of inductive reasoning problems. And you can think of it as each of these is a little discovery problem, and you need to figure out the rules that tell you how to assemble words in this language in new inflections. So here's an example of one of those problems. This is from a language called Saka. And there's maybe around 100 words here, and there's maybe around 6 different systematic patterns you need to make sense of this data. So you can use program synthesis to try to come up with the linguistic rules which act as a model for how to generate this data. So it's a generative program which tells you how do you build new words in this language. So for example, if you throw it at this data here, which says that in one inflection, a word like aron gets transformed to oronor, or ba gets transformed to ba-layer, it decides that the way you form this other inflection is by adding lar, which should be super weird because none of these suffixes are actually lar. And in order to make sense of this data, you need these extra rules. So these are synthesized linguistic rules, and each of them might look a bit cryptic if you are not familiar with this particular part of linguistics, but each of them can be translated into English and is like fairly interpretable if you're a linguist. So I said that this is a generative program. So each of these rules acts generatively. So jointly with some extra information, the stems for each of these words, this generates the observed data as follows. So if we want to produce the plural form of beds, you start with the stem for bed. You run this plural forming program, and then you iteratively run each of these rules. And these sort of edit the string and eventually tell you how to say this word. So these are the kinds of models and theories that people build in linguistics to explain like how you pronounce words in new languages. So you can do this for a wide range of languages. And what I think is most interesting is you can systematically change the programming language. So the underlying programming language that it's doing synthesis in is a kind of higher level knowledge, which tells it, this is what languages tend to look like in general. And what we see here is across all these languages, there's an important role for higher level knowledge. So what kind of programming language you give, which varies by the colored bar, strongly affects how well you can solve the problems from all these different languages. So here we're saying there's high level knowledge, and we're just systematically varying different hard-coded forms of higher level knowledge. So you might ask yourself, like, could we kind of do this higher level knowledge learning automatically? And the answer is sort of. So one thing that we tried doing is to start with data from a bunch of different languages, and then infer grammars for each of them, and then try to also infer something about the universal grammar. So we sort of baked in most of the universal grammar and then tried to learn like a little bit of an embellishment upon what we baked in. And just to kind of hint how we did this, and I'll explain in more detail later, the general idea was to do something kind of like expectation maximization, where you guess the stuff at the top, you alternate and solve for the stuff at the bottom, and you sort of do this until you converge. So I don't want to go into too much detail about how this alternating procedure works, because the rest of the talk is about a generalization of this procedure to other forms of programs. So I'll just say that we'll talk about it next. So the lesson here is really that higher level knowledge matters. In the case of linguistics, the higher level knowledge takes the form of what's sometimes called universal grammar. But at least a little bit of that higher level knowledge you can estimate from data. And in particular, we're running that, like I showed you the set of languages we ran this on, and it's a lot of languages, but it's not like a million languages. So it's sort of not a few-shot learning problem, but it's also not like a big data problem. So now I'll talk about the more general case of learning higher level knowledge. And I'm going to think of this as learning how to write code. So the higher level knowledge is about how to write programs. If you think about writing programs, there's at least two different things you need to know. One is you need to know the programming language. You need to have the right libraries, the right kind of symbolic structure that you're going to use to start for writing code. And also you need to know something about how to synthesize programs in the first place. So that's like a synthesis strategy, or you can think of this in like old school AI terms as like declarative knowledge and procedural knowledge. So I'm going to illustrate this learning of declarative knowledge of the symbolic language that we're going to do synthesis in a classic program synthesis domain, which is just learning functions which transform lists of numbers. So concretely, imagine that you needed to synthesize a program that sorted lists of numbers. So you might specify that by giving inputs and outputs. So you can think of this as some observed data, which tells the system that it should sort lists of numbers. And imagine that you start out with a fairly simple programming language, which has things like map and folds, and maybe conditionals, and maybe things from Lisp, like cons and car and clear. So somehow we need to bridge the gap between the initial programming language on the left and the problem on the right. So what the system does is it doesn't just try to sort lists of numbers. It takes the view that you never have one data set, you really have like a bunch of data sets, and you're trying to jointly understand all of them. These data sets are programming problems. Early on in the execution of this learning algorithm, one of the first things it does is it decides to define a new function in its programming language And I've written it out here. And what it does is it builds on top of this other function, fold, which was built into the system. And this function here, which was the fourth function it decided to learn, is sometimes called filter. It takes a predicate and a list, and it removes or filters the elements of that list which do not satisfy that predicate. So filter is really helpful for lots of things, but it's not really, it's not moving you that far towards sorting. So if you run this algorithm longer, what you see are other functions in its learned library of subroutines, which start to move closer to sorting. So one of the things it learns, for example, is how to calculate the maximum element of a list. And calculating the maximum element of a list seems like it's getting much closer to sorting. In order to do this, it had to build upon the fact that it already knew how to filter lists of numbers. So it started out with these primitives and then learned filter and then built on filter to learn maximum. And if you look at one of the very last things that it learns this subroutine, which calculates the nth largest element of a list. And having this thing in your programming language, so having this thing just be part of your built-in suite of higher level abstractions that you can use, is obviously really useful for sorting, because once you have concept 15, this routine, which gets the nth largest element of a list, it's super easy to write down a sorting algorithm. All you have to do is repeatedly call concept 15 and ask it to give you the first largest element, then the second largest element, then the third largest element, and so on. Now, the code that it wrote here is how it eventually comes to sort lists of numbers, but in theory, you don't need this learned library of functions. In theory, you could have just solved this sorting problem using the initial primitives that we gave it. Now, the problem with that is as follows. So if you take this code here and rewrite it in terms of the initial primitives, you get this mess that I'm showing right here. Now, this code here has two problems. One is that it's not very interpretable. It's so long and has so many little function calls that you can't, as a human, look at this and say, oh, I can tell that it's discovered how to sort numbers. The other sense that this is a problem is that it's not just uninterpretable, it's also kind of inaccessible. There's no reasonably bounded search you could do that I'm aware of, which would start with the initial primitives, start with these input-output examples, and then converge on this expression here. In particular, if you did a brute force search over expressions in the initial primitives, it would take far longer than the age of the universe to come up with this long, unwieldy sorting algorithm. It's much more efficient to learn the right higher level concepts and then use those high level concepts to discover how to sort lists of numbers. So what I'm going to do in the last part of this talk is explain the algorithm which acquired these high level concepts and then wrote this sorting algorithm. So this system is called Dreamcoder, and the reason why it has that name is because it's a program synthesis algorithm which is modeled after the architecture of wake-sleep algorithms, which are unsupervised methods for training neural networks. So Dreamcoder has what's called a waking phase, where it solves problems by writing programs, and this waking phase is interleaved with a pair of sleep phases. So during what I'm going to call abstraction sleep, it's going to improve its library of higher level functions. So it'll be adding new functions to that network of routines I was diagramming earlier. And it also has what I'm calling dream sleep, which is where it's going to train a neural network, which is sometimes called a recognition model in the wake sleep literature, which is going to help guide the search process over the space of programs. So concretely, you can think of this as a hierarchical Bayesian inference problem where we have a bunch of tasks to solve. So these might be input outputs, they might be like data from some unknown function, and we want to write a program that can explain each of those tiny data sets. And then at the highest level, these programs are united by a library which gives a kind of prior over the space of programs and imparts the right kind of high-level knowledge in order to make the discovery tractable. So one twist we're adding here over the prior works that I cited on the previous slide is we're training a neural network, the recognition model, which is going to make the combinatorial search problem easier. So if you look at this learning task here that I've diagrammed, there's really three things we don't know. We don't know the library, we don't know the programs, and we also don't know the weights of the neural network. And so the fact that there's three unknowns motivates a three-stage iterative learning procedure. And that's exactly what we do, and that's why we have these three phases to this algorithm, because there's three unknowns. So during what's called the waking phase, we're taking our current library and we're taking some task, so some data like input outputs, and we're having the neural network bias a search over the space of expressions built from the current library, and we search until we find a program which matches that data, or until we time out. During the dreaming phase of sleep, we're going to train the neural network, the recognition model, and this neural net has to be trained on pairs of programs and tasks. The issue, though, is that in this model, we only observe tasks. We don't observe programs. So somehow we need to infer programs so that we can supervise the neural network. The simplest way of supervising the neural network is just to replay programs that we found during waking. We can say we solved this task with this program, so train the neural net to predict that program when you see that task. But a much more interesting source of data is what's sometimes called fantasies, or randomly generated data. And the idea here is to take our library, which acts as a generative model or prior over the space of programs, and sample programs and run them to see what they do, and then use those as training data for the neural net. In order to do this, though, we need to learn the library, so the samples actually look like real programs. The way that we learn the library during the abstraction phase of sleep is to take programs found during waking and look at their syntax trees and try to compress out reused structure in those syntax trees. So it's a kind of process where we're mining it for abstractions. So in this example, there's these two common syntax trees, and we can pull them out and add them to the library. So by doing this, we gradually enrich the higher level knowledge that we're giving to the system. So we've applied this to a range of domains, and I want to briefly focus on a few domains here that illustrate how and why the system works and what role higher level knowledge plays in these program discovery problems. So for logo graphics, this is a domain where we give the system a picture, so pixels of some geometric design, and we ask it to write a program in a simple graphics language, which will draw that picture. So when you run Dreamcoder on this corpus of images, here's what happens. So on the left, I'm showing you some primitives from the initial graphics programming language. On the right, I'm showing you some images that I had to draw, and below each of them, the code it wrote in order to draw it. And in the middle is the higher level knowledge that it acquired over the course of its learning trajectory. So these are functions written in this Lisp-like language, which it found helpful in the process of drawing these pictures. So for example, when it's drawing this kind of swirly beach ball-like thing, it calls out to learn function 8 and also to learn function 4. Learn function 4 is a parametric routine for drawing spirals, and learn function 8 is a higher order function which takes another drawing routine and repeatedly runs that drawing routine while spinning around in a circle. So that makes sense because this swirly beach ball kind of looks like a spiral that's been spun around in a circle. Now, I think function 8 is really interesting because this really corresponds to the higher level concept of radial symmetry. So rather than bake in this higher level knowledge about radial symmetry, instead what we can bake in is knowledge about coordinates and loops, and then in an unsupervised way, in the course of drawing lots of radially symmetric problems, it is trying to abstract out these concepts. If you look at its learn library, you see other things which look more familiar, like circles and polygons, and other things which look less interpretable and which don't really correspond to any intuitive geometric concept that we might have already, but which are nonetheless useful for drawing lots of these pictures. So these functions represent kind of like its explicit declarative knowledge of what programs should look like, but it's also acquiring procedural knowledge of how to write code, and that procedural knowledge is embedded in the weights of its neural network. That neural network is trained on dreams or fantasies, which are randomly generated programs, and it's helpful to look at what those programs look like. So here are randomly generated programs at the initial state of learning. I've color-coded them to show how it draws each of these things. So it starts at dark blue and then goes to light pink. These are the most interesting samples from 150 draws because most of the samples from the initial library before learning are just either blank canvases or empty or a single line segment. So now we show the.
You have 4 minutes left.
Okay. So after dreaming, what you see instead is this kind of recombination of kind of like these higher level building blocks that are acquired from the training data. So because time is short, I want to just briefly show one other case where we applied Dreamcoder to something that looks more like a scientific discovery problem. So what we did is we took a bunch of equations from AP Physics cheat sheets and things like that. So equations look kind of like this, and we ran them with random inputs and outputs. And we told Dreamcoder, try to fit the data from each of these equations. So there are around 60 equations. And the main twist here is that instead of telling it about vectors, we instead told it about lists of numbers and asked it to sort of build stuff that can model these equations, but without knowledge of vectors. So if you look at the very first things that it learns, the very first thing that it decides to add to its higher level knowledge are routines that perform basic vector algebra. So things like adding and subtracting vectors or calculating vector norms. And if you look deeper into its learned library, we start to see our routines that implement higher level knowledge that look more like physics. So things like integrating second derivatives over time. And if you look at sort of the final layer of its learned library of functions, what you see are things like schemas for things like inverse square laws. And once it has these routines, it's much easier for it to solve these problems. So for example, when it's solving the Coulomb's law problem, it calls out to its inverse square law schema and passes it the displacement vector from its subtract vectors routine. And this is, I think, fairly interpretable and kind of close to how I would think about Coulomb's law. But if you were to rewrite it in terms of the initial primitives, all of a sudden, it's no longer as interpretable and no longer as clearly connected to what Coulomb's law is kind of like really about. Like it's no longer really getting at what I would think of as being the true latent concepts that underlie Coulomb's law. I think there's a few lessons that you can take from this. One is that programs can act as a representation for discovery problems. The other is that this higher level knowledge can help make some of this tractable by making it so that you're operating over more abstract and more high level building blocks. And this effectively decreases the amount of code you need to write, and that makes the synthesis problems tractable. And the last is that we find that by learning these high level building blocks, you not only make things more tractable, but you also get more reusable abstractions that are easier for humans to understand and interpret. And ultimately, if we're trying to do discovery, then we want the machine to output some kind of formal representation that we as people can understand and comprehend and ultimately build on. So that's it, and thank you for your attention.